So for anyone who's watching the recording, sorry I forgot the microphone until just now. We're going over exam stats. All right, so I guess any questions about the general distribution of the exam before I start going through the key? Okay, cool. All right, so I'm more or less going to go through this in order, but maybe I'll skip ones if it seems like people more or less nailed it. Okay, so let's do number 1 here. Okay. Wow. Okay, so here's the compound we're looking at for problem number 1. And so it asks you assign R and S to all the stereocenters, or to all the asymmetric carbons. Draw the enantiomer and then say how many diastereomers it has. Okay, so looking through this, first of all, we need to identify where the asymmetric carbons actually are. General rule of thumb, you can't assign R or S unless you have some information about bold and dashed bonds. So the locations where those are shown are kind of your first place to start investigating. This carbon here has an H, an oxygen with a carbon, an oxygen with an oxygen, and then this entire ring. So that's 4 separate groups. So that's asymmetric. This one has an H, a carbon with a double bond, a carbon with an oxygen, and a straight up oxygen on it. So that's asymmetric. And then this one has an H, an O, a carbon that's one away from a carbonyl, and a carbon that's one away from an oxygen. So that's all 4 separate groups. So that's asymmetric as well. Okay, so nowhere else on this molecule is an asymmetric carbon. And even if it were, we wouldn't have bold and dash to be able to figure out what it is anyway. Okay, so 3 asymmetric carbons. Let's do this one over here first. So assigning priorities to the groups, I got 1, I got H, carbon, oxygen, and oxygen, which means immediately priority 4, priority 3. Oxygen versus oxygen is a tie that we haven't really seen before, but we can still apply the same rules as normal. This oxygen has a carbon on it. This oxygen has another oxygen on it. So this is 1, this is 2. Okay. So then we want to check group 4 is in the back. It's not. So let's pretend that's true for now, and then we can flip whatever answer we get. So we go 1 to 2 to 3, back to 1. We're going clockwise, which would make it R, but before we swapped it, it was S. All right. Sorry? Why did, like, when you swap, this direction still stays the same as if you hadn't swapped, so why do you change the direction? So another way to look at this is group 4 is coming out towards us. So if I wanted to just, without doing the fake swap, wanted to like mentally rotate the molecule, imagine I'm standing like in the far side of the board looking out with the molecule in front of me. And now if I go 1 to 2 to 3, back to 1, sorry, if I'm going to 2 to 3 here, so I'd have to go 1 to 2 to 3, back to 1. So I'm going counterclockwise as I'm looking at it from the wrong side. So it should be S when the H is positioned correctly going away from me, if that makes sense.
So if the H is coming towards you, the direction that like you draw is actually opposite.
Okay, so this one's S. I'm going to erase the numbers to keep it clearer as I do the other 2 in this molecule. Okay, so now let's look at this bottom one. Assigning priorities, I got H. I got carbon and oxygen. So oxygen wins first place, H wins last place. And then off of here, this carbon has an H and 2 bonds to carbon. This one has an oxygen, a carbon, and an H. So this top one wins priority 2, and this gets 3. Okay, so I think the way the stereochem was shown here threw some people off. A few people said it's not tetrahedral. It is. If you remember, like at the start of chapter 6, we covered a few ways to draw tetrahedral stereochemistry. And one of the options was you can draw 3 bonds looking like they're in plane and then one sticking out towards you. And sort of the, I guess the implication here is that all 3 that are like in plane are not exactly in plane. They're like going slightly away from you. So in other words, showing 3 in plane is really like 3 are slightly away from you and 1 sticking like directly out towards you like that. Okay. So what this means is that if you want to use the fake swap method here, you can swap H with any one of the other 3 and you'll still get the right answer. Or alternatively, you can do the same thing where you imagine that you're looking out of the board at the back face of this molecule, and then you sort of travel a track around, and then whichever way you go, you don't have to flip. Okay, so let's do fake swap just to get H going away from us. So we can swap it with any one of the other 3 and still get the right answer. Let's just swap it with oxygen up here. I'm going to say H, you're really 1 for now. Oxygen, you're really 4. I go 1 to 2 to 3, going counterclockwise. Therefore, it was R before I did the swap. And again, you get the same answer if you're pretending to look at this from the back. I've got oxygen, carbon. I've got group 1, group 2, group 3. So I'm going clockwise as I'm looking at this from the underneath. So I should still get R either way. Or alternatively, since you're allowed to use model kits on the exam, if you can't do either of those methods or don't trust your work, you can always just build this thing and then fiddle around with it in space and see like what you end up getting once group 4 is away from you. Okay, so questions about that one? Okay, cool. So then again, I'm going to erase the assignments here just to keep things a little clearer. Okay, so the last one, I've got H versus O versus C versus C. H is 4, O is 1. Over here, I've got a carbon with a C and 2 H's. Here I've got a carbon with an O, a C, and an H. This direction wins, 2. This one gets 3. Okay, so again, I can swap group 4 with any of the other 3 groups, and it'll still be going slightly away from me. So 1 and 4, and now if I go 1 to 2 to 3 back to 1, I'm going clockwise, so before the swap it must have been S. Okay, so S, R, and S are the 3 stereocenters in that molecule. Any other questions about that part so far? Okay, cool. So then the enantiomer, if you remember, that means, drawing the enantiomer means that we're flipping every stereocenter to its opposite. So S turns to R and R turns to S. Easiest way to do that is just straight up draw the same molecule as it is here, but every bold becomes dashed, every dashed becomes bold. So a few people tried like actually flipping the whole thing over, which is fine if you draw the bold and dashed correct, but honestly, the low effort way of doing this is just turn these bonds both to dashed. This becomes dashed, and that becomes bold. Okay, so that's the enantiomer. So we've got the original molecule and its enantiomer. And then the question asks, how many diastereomers does this molecule have? All right, so I guess this is a different question from how many total stereoisomers are there of this molecule, which I think threw a few people off. So total number of stereocenters is 3 in the molecule, which means the total number of stereoisomers with that connectivity is going to be 2 to the 3. which is going to be 8. But of that 8, not all of those are diastereomers to that original molecule. So I specifically asked how many diastereomers does this molecule have? Of this 8, 1 is the molecule itself. That's not a diastereomer of it. That's identical. And then 1 is the enantiomer, which is also not a diastereomer of it. So of the 8, that's going to be this molecule plus its enantiomer plus all of the rest of those 8 are going to be diastereomers. So the correct answer is 6. Okay. So questions about that one? Okay, cool. So I guess like if you're wondering like what's the closest analogy to this that we saw in lecture, probably it's going to be comparable to, if you remember that one where I drew up like bold OH, dashed OH, bold and dashed and bold. So this one is enantiomers with this one, but it's a diastereomer to the other two. So if I asked, like, here's a molecule, this specific one in this top left corner, how many diastereomers does this guy have? Then the answer would be 2. It's got 2 different diastereomers. So out of the 2 to the 2, or the 4 that are possible, that's itself, it's an enantiomer, and then however many others are there in the set. Okay, questions about that one? Okay, cool. All right, so 2, some parts of this people did pretty decent on, some parts were a little trickier. Okay, so Newman projections for the first one. It looks like a few people sort of drew those back into their regular zigzag form, but you honestly don't even have to go that far. If you just do, okay, HFBr and HCH3OH versus okay, so we know that what we want to do is compare all the asymmetric carbons like pairwise between the 2 molecules, and then like if all the same, they're identical. If all flipped, they're enantiomers. If some are flipped and some are not, diastereomers. So let's just straight up look at this front carbon in both ones first. I've got the H up top, bromine on the left, F on the right. And here it's the opposite, H up top, bromine on the right, F on the left. So in other words, I've swapped the bromine and the F between these 2 Newman projections. So in other words, the front C flips. And then meanwhile, the back C stays exactly the same, CH3 and H and OH. Okay, so this tells me 1 stereocenter flips, 1 stays the same, which makes them what? Yeah, diastereomers. Okay. Okay. So then B. Okay, so this one, I think a few people started out trying to flip the molecule over, which you can do if you want. But it may be quicker and easier to recognize that in this one, the double bond is like on the opposite side of the ring from where the methyl is. And in here, it's 1 closer to where the methyl is. So these don't even have the same location of the double bond. They don't have the same connectivity, which makes them what? Yeah, constitutional isomers. Okay. All right, so C I think was the trickiest one because I got deliberately fancy with how to draw it. Okay. So this one, okay. This one, it definitely helps to redraw because if you redraw everything as zigzag format, remember that ethyl is going to be a 2-carbon chain. The ET is CH2CH3. So if you draw that in here, it looks like this. I think a lot of people just saw ET and they're like some other element that I don't recognize that's different from a CH3, therefore different. But remember that this is still, indicating some alkyl group that may still match up with part of the chain. Okay, so this is not actually drawn in the same layout as the other molecules, so we got to rotate it around a little bit first to see if it's the same. Let's go ahead and spin this around. All right, so I got a methyl that's sort of sticking up and out of the board. If I want to grab it and push it down into the plane of the board, I'm doing a little bit less than 180-degree rotation, which means that meanwhile, this end of the chain here is going to start flat in the board and is going to rotate around to up but pointing back. Okay, so that might be a little hard to see if you can't mentally rotate stuff, but building a model kit might get you through there. Okay, so, and I could have done the same operation on this thing and gotten its methyl group to stick up instead. Either one you fiddle around with is okay. Okay, so now that I've done that, I can check, okay, bromine's dashed and dashed. This up-pointing ethyl group is dashed here and dashed there. So these are actually identical. Okay. So I guess if you tried building models of these, you were probably more likely to see that right off the bat. Or if you tried assigning like R and S to these, you might have realized that this is like a 2-carbon chain. I guess, yeah, aside from that, I don't know if I have any good tips for like how to see that immediately. But once you catch on that you can draw them differently, then you can start playing around with them and twiddle the bond angles a bit. So, okay, questions about that one? Okay, cool. So D, I think this one most people got. So I've got, comparing pairwise, I've got fluorine dashed and bold, so that changes. Bromine's dashed and dashed, that stays the same. Bromine's bold and bold, that stays the same. So these are diastereomers. Okay, any questions about that one so far? Okay. Okay, so these two threw some people off as well. I guess it helps to remember that like hierarchy of relatedness because these two have the same connectivity, but they're not superimposable and they're not mirror images, which means sort of by default they fall into which category? Yeah, diastereomers. So I actually covered a cis versus trans alkene example after doing that, which just showed that, yeah, those are technically considered diastereomers, even though they don't have any asymmetric carbons on them. Okay, and then The last one, surprisingly, really threw a lot of people off. Okay, so both of these have 6 carbons, and I saw a few people who got it right, the formula underneath it, so 6 carbons and then 12 H's. Same as 1, 2, 3, 4, 5, 6, C6. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So H12. So they have the same formula, but totally different connectivity, which makes them what? Yeah, constitutional isomers. And a few people cleverly didn't even bother counting the hydrogens and instead looked at number of carbons and degrees of unsaturation, which will save you some work. So 1 degree of unsaturation here, 1 degree of unsaturation there. They should have the same formula if they got the same carbons. Okay, so questions about that one? Okay, cool. How are we doing on time? Okay. Okay, so it looks like some people, or some parts of number 3 people did really well on, and some parts were a little bit tougher. So I guess let me run through all 5 letters and people raise their hand if they want me to go over it, and then I'll pick maybe like the most popular ones. Who wants to cover A? Okay, who wants to cover B? B, okay. C? Okay, a few hands for C. D? No. E? Okay. Okay, so I'll do, I think, B, C, and E. All right. Okay. So for this one, okay, so we want an OH added on there. And given that there's pretty much no possible way to have an alkene coming out this direction from the carbon, pretty much the only location we could have had an alkene in the starting material is going to be this. So am I going for Markovnikov or anti-Markovnikov style addition to that molecule? Markovnikov, right? I want to add something to the more substituted carbon. So in theory, I know 2 different reactions that'll add an OH and an H, Markovnikov style, and that's acid catalyzed hydration and oxymercuration reduction. But what's the problem with one of those? Yeah?
If you use acid catalyzed, then you'll get a hydride shift.
Yeah, exactly, or carbocation rearrangement more generally. Yeah, so if I used acid catalyzed hydration, I'd make a carbocation here. One of these methyl groups would immediately hop over, and I'd rearrange the skeleton of the thing, which I don't want to do for this particular reaction. So instead, I got to use oxymercuration. I guess if you skip ahead to problem 4, I actually give you what reagents you need for part 1 of that on the arrow, so you could straight up just copy that over from the next page. Didn't give you step 2 though, so that you got to know unfortunately, but sodium borohydride and then some kind of OH source like NaOH. Okay. So as a reminder, it's got to be a 2-step process. You lost 1 point if you didn't sequentially number the steps. I think the way the grader split this one up is 3 points for the starting alkene for each of the problems and then 2 points for the reagents. Okay, so questions about that one? Okay, cool, let's go into C. Okay, so this one, again, there's pretty much only one possible place you could have had an alkene wedged into the starting material, and that is like the only 2 carbons that could both lose an H and have made a double bond between them as we're working backwards. So I guess if you're looking at this, you're trying to add an H to both ends of the double bond. So we're trying to do a hydrogenation. So H2 and palladium on carbon. I saw a few people get a little bit creative with the catalyst for that. Just as a reminder, this is a D, not a B. I saw a few people use lead on carbon, Pb on C, but it's got to be palladium or platinum. Okay. Any questions about that one? Okay, cool. So E is the tricky one. Okay. Okay. So a few parts to this. One is that we have to start with a hydrocarbon, so something that's all C's and H's, and it has to have the same number of carbons as our final product. So what that means is that all of these oxygens must have gotten added on during the reaction, including this OH at the end, which tells us that, I guess first of all, what kind of general reaction we're using has got to be pretty much the only one that we've seen that will add carbonyls. So it's going to be ozonolysis. So O3 should have been your first step. And then the second step, you have to make another decision. We know that this OH must also have gotten added during the reaction, which means that for the second part of ozonolysis, we want what on the arrow? Yeah, good. Water and hydrogen peroxide, H2O and H2O2. Okay. So working backwards, we know that this stuff will replace any H's at the base of a carbonyl with an OH. Oops. Which means that, just to sort of do some scratch work over here, if we'd done DMS instead, it would have looked like that. Okay, which is kind of how we want to figure this out working backwards. Okay, so then we're looking at this and we're like, okay, all the places where a carbonyl is attached now, that must once have been part of an alkene. I can't straight up double bond a new carbon onto there though, because then I'm changing the carbon count in the molecule, which I know is not something the problem wants me to do. I want to keep the same number of carbons. So instead what I got to do is straight up double bond these two guys to each other. All right, and so people had some interesting bond lengths and angles going on here, but as long as you got the connectivity right, it was totally fine, even if it looked really wonky. I think I saw when I was flipping through, some people just straight up drew a double bond like this, which is a very long bond, but technically that is correct connectivity-wise. If you want to get this thing relaxed into a more natural looking shape though, you've got a few options. One is draw this as like an internal bridge holding the ring together, sort of across the middle. But remember that one of these carbons has a methyl coming off of it and the other just has an H, which we're not going to show. Or you could show it as we're going to keep the six-membered ring the same, and we're going to double bond these two guys together below the ring. I think I saw about equal amounts of these two flipping through, but I didn't grade that one, so I didn't have a good sampling.
If you wanted the second step to involve the input instead of the hydroxide, could you have in your starting material included an OH?
So two problems. One is you got to start with a hydrocarbon according to the problem, the way it's phrased. And the other one is for reasons that we're going to cover. So let me actually draw what Anna's asking, is that is, could we use this? Partly I ruled that out by the phrasing of the problem. And the other part is, for reasons that we'll cover in OChem 2, this thing doesn't last very long. It actually immediately rearranges itself to a carbonyl instead. So yeah, even if that looks like a viable starting material, it turns out it's not going to sit around for very long that way. Okay, so questions about that? Yeah. Okay. Alrighty, awesome. Okay, so how about number 4? I'll do the same thing with the letters. So we got parts A, B, and C. Who wants to cover A? Okay, who wants to cover B? Who wants to cover C? Okay, A and C seem like the most popular. Okay. So for A, we've got BH3. Okay, I guess one sort of general heads up on this question is there's several parts of mechanisms or like steps of reactions where I didn't cover the mechanism for them. So like oxymercuration reduction, I only covered the mechanism for oxymercuration but not for reduction. And hydroboration oxidation, which is this one, I only covered the mechanism for hydroboration but not for oxidation, which is why I'm only showing you the reagents for the first half of the reaction, so you're not going to go all the way to the end of the final products for this. Okay, so if you remember, the way that this works is the boron has an unfilled octet. It's got space for extra electrons coming in. So when the attack comes from the alkene, it's going to go straight there. But if that were all I did, this carbon would be left missing electrons. It would have a positive charge. And so the boron can actually give up electrons, not from any lone pair that it has, because it doesn't, but it can drop an H bond, which will slide over there as a hydride. So this is like a concerted, we'll cover a little bit more about that later on, but everything's happening at once. And so you end up with H here and BH2 there. Okay, so this has got to be an anti-Markovnikov style addition, in other words. A few people remembering the thing that I covered in lecture of this can happen up to 3 times per molecule went ahead and did exactly that. But again, if you read the phrasing of the problem, assume each molecule of reagent reacts with only 1 molecule of starting material. So you're actually good to stop here. Like this is just a one-step mechanism. And you get to here. If you assume that no other molecules of starting material go on to react with it, then nothing else is going to happen until some future time when we would bring in reagents that we don't actually have on the arrow here, and then we could maybe finish up the oxidation. But this is actually all you got to do for this problem, is the hydroboration. Okay, questions about that one? Okay, and then so B was reasonably kind of, I think most people did okay on that one. C, same starting material, and then Br2 and CH2Cl2. All right, so I think writing this in here explicitly kind of threw some people off. What's another name for this thing? Yeah, DCM. Dichloromethane. It's a solvent that you use in lab. Yep. So I guess sort of, even if you didn't remember that, you could figure this out in terms of like, okay, all the variations of this reaction we've seen where the solvent comes in and attacks, it's because it has an oxygen with a lone pair that does the attack, and then later on that oxygen gets a proton pulled off. That's what gets it back to being neutral, and that's what allows it to stay as part of the molecule. DCM doesn't have that. It does have lone pairs that it could hypothetically attack with, but then there's no way to like deprotonate the chlorine afterwards, so then it just kind of has nothing to do but fall right back off. Okay, so DCM here. I guess also if you worked through the sapling problems or the recommended textbook problems, they had a few versions of this where they explicitly listed DCM as the solvent and then it didn't do anything in the reaction. So that's kind of another chance that you might have had to catch this, even if you didn't figure it out like right from looking at it. Okay, so this one, anytime we have a dihalogen here, We want to start the reaction out with the alkene attacking, dropping the other bromine, and then the lone pair back attacking to form the bromonium ring. Okay, and then at this point, a lot of people showed DCM coming in and attacking, but also a few people mysteriously had water and alcohol showing up out of nowhere. Don't do that. If I give you limited reagents on the arrow, you got to use those, sorry. Okay, so at this point, the Br minus will come in, pop the ring open. Okay, and note that when the attack happens, it's going to be on the more substituted carbon, not the less. So if you attacked here, I think you lost 1 point out of 6. And if you had an arrow missing to make the ring, I think you also lost 1 point out of 6. Okay, questions about that one? Okay, so that's kind of a good place to wrap up. The key's posted online and your score should be in Canvas. I guess let me know if you've got any questions, but otherwise I'll bring the stack of exams with me on Friday, so anyone who's not here today can pick them up.